Now let's talk about representation of binary tree. Okay, so far we talked about the binary tree as an abstract data type. Okay, so we use the graph. Okay, so do you remember when we talked about list? Okay, and we talked about the abstract data type of a list. Okay, and then we used an array to represent a list. Okay, and also we use the linked list. Likewise, for binary tree, then we will use a couple of different representations. First one is array representation. Okay, so in this array representation, we will store nodes in an array in order from top to bottom, left to right. Okay, so given this figure, given this tree, then these nodes can be represented by this array. So root node will be the first element of this array, and the left child of the root node will be the second element, and the right child of the root node will be the third element. So we just count all the nodes from the top to the bottom, from left to right. Okay, so these numbers will be the index of this array. This is quite a simple representation of binary tree. When the binary tree is represented by an array, then we can take advantage of the structure of an array. Okay, so here's a lemma. If a complete binary tree with n nodes is represented sequentially, it means array. Then for any node with index I, we have these three properties. First, parent I is at and the flow of I divided by 2. So this is a flow operations. It means when I is 2, then it is 1. But when I is 3, then it will be 1, 2. So 1.5, the flow of 1 point something will be 1. Okay, and only when I is not 1. If I is 1, it means I is at the root node and has no parent. So we don't care that. So the parent of one node can be simply calculated by these equations. Okay, something like this. The node index is 2, then the 1 is the parent. When the node is 5, then 2 is the parent, like that. So we can find the parent of any node quite easily. Okay, so simple. And second, left child of I is at 2 times I. If 2 times I is less than or equal to n. Okay, and if 2 times I is greater than n, then I has no left child. So imagine one a binary tree, and let's say I is 2. Okay, then who is the left child? The left child is 4. It's a simple. I is 3, then the left child is 6. Okay, and if 2 times I is greater than n, it means it doesn't have a left child. Okay, so it means it is a leaf node. Okay, and what about the right child? So right child of I is at 2 times I plus 1. So look at the second one, left child and right child. So if the left child is 2 times I, then obviously the right child should be at 2 times I plus 1. Okay, and only if 2 times I plus 1 is less than or equal to n. If 2 times I plus 1 is greater than n, then I has no right child. Okay, so if you get confused, then draw some binary trees and check what these statements mean. Okay, so proof is quite simple. Okay, and if we prove the second one, and then based on the induction, and then the first one and the third one will follow. It's kind of straightforward. Okay, let's prove the second one. So baseline is, so we have to start with base case. Okay, for I is 1, so which means we are talking about the root node, and the left child should be at 2. Okay, so root node is at 1 and the left child should be at 2. And we have hypothesis, induction hypothesis says for all j between 1 and I, and left child of j is at 2 times j. This is our hypothesis. Let's assume that this is true. Then induction step says that left child of I plus 1 follows 2 children of I. Okay, so we are talking about the left child of I plus 1. Then and then the left child of I plus 1 should follow 2 children of node I. Okay, so then the left child I plus 1 is at 2 times I plus 2. Because 2 times I is actually the index of the left child of I. Okay, so left child of I plus 2. That is 2 times I plus 1. So we proved it. Left child of I plus 1 is 2 times I plus 1. So we just proved it. Okay, in this slide we have 2 examples of array representations. So first one is a complete binary tree, and second one is a skewed binary tree. When it is a complete binary tree, then it is perfect. So from the first element to the 9th element, we can represent all the nodes. Okay, but if it is a skewed binary tree, then we need lots of empty cells. Okay, so basically we have only 5 nodes, but it goes from 1 to 16. Okay, with lots of empty cells. So let's try a couple of nodes. Okay, so A goes to the first element. Okay, and the B is the second. Perfect. But we don't have the right child of A, so we skip. So the index 3 has nothing. And then now we have C. Okay, and C is at 4. And then what about 5? So B doesn't have a right child. Okay, so 5 has nothing. And what about 6? 6 should be the right child of A is A's right child's left child. Okay. So we miss lots of nodes on the right side of this figure, right side of this tree. So we have lots of empty cells in these array representations. So we are wasting lots of memory space. Okay, so that's not efficient at all. So only when the tree is complete, okay, then we can use the memory space in an efficient way. But sometimes we have this skewed. Even though the one binary tree is not that skewed, not as skewed as this example, but sometimes we don't have a complete binary tree, then we waste lots of memory space. Okay. Now let's talk about the linked representation of binary tree. So when we were talking about list, we talked about array and we talked about linked list. And when we were talking about stack, we used an array and we used a linked list. Likewise, in the previous slide, we talked about the binary tree with an array, and that is not great. Now we will talk about linked representation of binary tree, as we have done a couple of times with other data structures. Okay, so now each node has data and 2 pointers, okay, to left and right child. And the structure can be defined in this way. So in this tree node, we have a data. Okay, this data is just integer. Okay, to simplify the implementations, we use just integer, but it could be a structure. Okay, another structure is something like element. Okay, so element and data. Okay, and more importantly, we have a left child pointer and right child pointer. And as I said, the reason why we are learning the data structures is to manage the data more efficiently. So this data part is more important actually, but we don't talk about the content in the data structure class. We talk about the structure. Okay, so this left child and right child, these pointers are important in the implementations, but Okay, don't get me wrong, the data is more important. Okay, but we will not talk about data much in this data structures class. Okay, so this is our structure for a binary tree node. This corresponds to one node. Okay, so with this box representations, we have a left child, data, and right child. Or in this tree representation, we have a data node and two arrows. Two arrows represent two pointers. When we have a linked representation for a binary tree, then it looks like this. So root is pointing the first node, the root node of this tree. And the A is the data, and the A node is pointing the B with the left child pointer, and the right child pointer is null. And B has the null pointer for the left child, and the right child of B is pointing C. And the C has null pointers. Okay, so left child and right child pointers are null. And in this box representation, it looks like this. Okay, so root is pointing this block, and the left child pointer of the root node is pointing B node. Okay, so etc. Okay, let's compare array representation to linked representation. Actually, we did the same things with the list, right? So we compared array representation and the linked list representations. Okay, so remember that, and then we will apply the same kind of rules here. Okay, the first criteria is finding locations of parent and children. Okay, so with an array representation, this task is really easy. So we had a slide about this. Okay, so given a node index I, then the parent is given by the flow of I divided by 2. Okay, for example, if I is 7, then the index of the node is 7, then the parent of that node is at 3, right? And the left child of that node is at 14, and the right child of that node is at 15, if any. Okay, so it's easy. So given a node, then we can find parent and left child and right child so easily. But with the linked representations, it is a little complicated. Okay, so given a node, then the left child is easy to find and right child is easy to find. Okay, so we have two pointers. Okay, no problem. But what about the parent? We don't have a parent pointer in the structure, so we cannot point the parent. Then when we have one node, then how can we find the parent of that node? It's not that simple. Okay, so we will talk about it later, but for now there is no way to do that. Okay, the second criteria is about the space overhead. Okay, so in the previous slide we talked about array representation of a binary tree with two examples, right? So if it is a complete binary tree, then we don't waste any memory space. But that's not general case. Okay, that's kind of special case. In general, it wastes lots of memory space. Okay, so if one node doesn't have a right child or left child, then that part is missing in the array. So we have lots of empty cells. But with the linked representations, we don't waste that kind of memory space. Okay, so but we have a little space overhead because we need two pointers. Every node needs two pointers. Okay, so every node needs 8 bytes. If it is a 32-bit system, then the one pointer needs 4 bytes. And then since we have two pointers, so each node needs 8 bytes. Okay, in addition to the data. But compared to these array representations, this is just a little. Okay, and the next one is computation cost for insertion and deletions. So as we've seen in the array representation of list, then whenever we insert or delete, then we have to shift some part of this array representations, right? So it is expensive. But with the linked representation, we don't have to shift anything. So whenever we insert or delete, then we have to adjust a few pointers. Okay, so computationally, it is inexpensive. Okay. And as I said before, the memory access is really expensive in the computation. So we have to minimize the number of memory access as much as possible. Okay. Before talking about any operations of binary tree, then let me give you a brief kind of big picture of this binary tree class. Okay. So bin tree is a class name, and we have a private member, tree node pointer root. So it's basically the same thing. Okay, so in the stack we use the hat. Okay, so as a private member we had a list node hat or top. Okay, likewise we have a tree node pointer root. Okay, this is a pointer, and we have lots of public member functions, constructor, destructor, and it's empty and make bt. We talked about these functions when we talked about the abstract data type of binary trees, right? So make bt and lchild, rchild. Sometimes you want to copy, okay, and sometimes you want to insert one node, and sometimes you want to delete one node, and sometimes you want to compare the two subtrees, okay, or sometimes you want to compare this tree, this binary tree to other binary tree. Okay, sometimes you want to print. Okay, so this is the class definition for a binary tree. Now let's talk about a couple of operations of binary trees. Okay, first one is traversal. Okay, traversal is visiting each node exactly once, and this operation is closely related to expressions. Do you remember we talked about infix notation and postfix and prefix notations? Likewise, we will do the same thing here. So we have three possible orders of traversal at each node. Okay, first one is in order traversal, and second one is pre-order, and the third one is post-order. It's exactly the same as infix notation and prefix and postfix notations. So given this figure at the bottom of this slide, an in-order traversal will traverse the left subtree first, and then root node, and then right subtree. And it corresponds to A plus B with this simple tree. And the pre-order traversal will traverse the V first, the root node first, and then left subtree, and then right subtree. And it's like plus AB. Okay, so we read the root node first, and then we read A and B. And the post-order traversal traverse left subtree first, and then right subtree second, and then the root node. It's like a B plus. Okay, so if you understand the infix and postfix and the prefix notations, then this is kind of the same thing. You know this slide, right? So in the basic concept chapter, we talked about the recursive algorithms. So basically, recursive algorithm is powerful to handle a complicated problem. So it can find a way to divide a problem into subproblems whose solution is the same with the original problem with reduced size. Okay, refresh your memory. Okay, and then we will use this recursive approach a lot with the tree operations. And we'll talk about the binary tree traversal. And remember, the structure looks like this. We have a data and the two pointers. Okay, that's the structure. And the tree is given like this. Okay, and then we will check all the nodes exactly just one time. Okay, first one is in order traversal. So basically we will traverse the left subtree first and then the current node and the right subtree. Okay, so this is a member function of this binary tree. Okay, so we get one pointer, PTR. So basically this one is pointing the root node of a subtree. Okay, so initially we will get the root node. Initially we will get the root pointer. Okay, and then if PTR is not null, which means it is not the leaf node. Okay, so it is not it is pointing something. Okay, then first we will call in order function with passing the left child. Okay, so PTR left child is pointing the left subtree. So we will do this. We will do this in order traversal with the left subtree first, and then the current node. Okay, so instead of doing something else, we just print out the current node. Okay, and then after visiting the current node, I mean printing the current node, and then we call in order functions recursively, passing the right child pointer. Okay, so recursively we will visit the left subtree and the current node and the right subtree. That's it. And if we print out, then we will get A/B times C times D plus E for this figure. Okay, so it is in fixed notations. And in this figure, I think the numbers are not correct, so ignore the numbers. Okay. And second one is a pre-order traversal. Okay, so we'll visit the current node first and then left subtree and the right subtree. Okay, in these functions we get one pointer as before. Okay, and then we'll check if PTR is null or not. As long as PTR is not null, then we print out the current node's data first, and then we will call pre-order passing the left child pointer, and we'll call pre-order passing the right child pointer. So basically we visit the current node and we visit the left subtree and then the right subtree. So if we print out the result given this tree, then the result is plus star star slash A B C D E. Okay. And the post-order traversal is exactly the same as in-order and pre-order traversals, except the order here. Okay, so we visit the left subtree first, and then right subtree, and then the current node. And in these member functions, we get one pointer, and we check if it is not null. Then we call post-order functions passing the left child, and then we call post-order function passing the right child pointer, and then we print out the current node's data. Okay, and if we print out, if we run these functions, then we will get A B slash C star D star E plus. This is exactly the post-fix notation. Okay, this slide compares three different orders. Okay, so in the in-order traversals, we visit the left one first and then the root node and then the right one. And in the pre-order traversal, we visit the root node first and then left. Okay, in the left subtree, we visit the root node first and then left and then right. Okay, in the post-order traversal, we visit the left subtree first and then right subtree, and then the root node. Okay. In this slide, we implement in-order traversal iteratively. So we already talked about the recursive solution for in-order traversal, which was really simple. But in this slide, we will implement that iteratively. Okay, so as in the recursive solution, we get one pointer, PTR. Okay, and then we declare one instance of stack. Okay, and then in the first for loop we iterate infinitely, and then in the second for loop, okay, PTR is moving to the next left child. Okay, and then we push the current PTR. Okay, so as long as PTR is not null, we push the current PTR and we move to the left child. So with this figure, we push 2, okay, and then we push 7, and then we push 3, okay, and then we meet null, then we quit. So now in our stack, we have 2, 7, 3. 3 is at the top of the stack. And now after the second for loop, we pop. So now PTR is pointing 3. And 3 is not null, okay, so we don't break. If the stack is empty, then the PTR will be null, so we will break. So now PTR is pointing 3, so we print out 3. And then PTR moves to the right child, which is null, but okay, so PTR is pointing null. And in the second, we go back to the top of this first for loop. And in the second for loop, since PTR is pointing null, then we don't push anything. And then after this for loop, then when we pop, PTR is pointing 7, okay? Now PTR is pointing 7, which is not null, so we print out 7 and we go to the right child, which is 6, okay? So now PTR is pointing 6. So we go back to the top of the first loop. So in the second for loop, we push 6. Okay, and then we move to the left child 5, and then we push 5, and then we move to the null. So we quit, and when we pop, the PTR is pointing 5. Do you see that? So every time, you know, we move to the left child, and when we move, actually we push the current node and we move to the left child, and the left child and left child. And then we pop and we print, and we move to the right child, and then we pop. Okay, so based on this stack, we can traverse this graph in order. So left child first, and then the middle one, the root node, and then right subtree. It's a little more complicated than the recursive solution, right? That's why recursive solution is much more powerful to implement. So far we talked about 3 different orders for traversal. So now we have another kind of order traversal, which is level order traversal. Okay, so basically we visit the nodes at each new level from the leftmost node to the rightmost node. For example, given this tree on the right side of the slide, given this tree, the output is plus star E star D / C A B. So we visit the first level, and then second level, and the third level, fourth level, and fifth level. And at each level, we visit the leftmost one first, and then move to the right one. Okay, so that is a level order traversal. So in these implementations, we use queue instead of stack. Okay, so we get one pointer as a parameter, and we declare one queue. We declare one instance of queue, and if PTR is null, then we return. We don't do anything. And first we add PTR. So plus, actually we are talking about the pointers, not the data. Okay, don't get confused. In the previous slide, we used the pointer too. So for the first time, we add the first pointer, which is pointing the plus node. So I will just use the data, okay? So we just add plus node, pointer to the plus node, okay? And then we go into this for loop and we delete. So now PTR is pointing plus, and PTR is not null, so we print out plus. And then if it has the left child, then we add the left child to the queue. And if we have the right child, then we add the right child to the queue too. So in this example, in the first iterations, we print out plus and we add a star and we add E. Okay, and then go back to the top of the first for loop, and when we delete, it will be star, actually pointer to the star. Okay, and then it's not null, so we print out star, and then we check if the left child pointer is null or not. So since it's not, so we add star to the Q, and then the right child is pointing D, so we add the pointer to D to the Q, and then we go back. Okay, now we printed out plus and star, and in our Q we have E star D. Again, we have the pointers in the Q. Okay, so pointers to E and star and D are in the Q. Now when we delete, then we get the pointer to E. Okay, and then we print out E, and the left child is null and right child is null. Okay, the left child and right child of E are null. Okay, and then we don't add anything, and we go back to the top of the for loop, and when we delete, we get the pointer to star. Okay, and then we print out star, and then we add slash, and we add C, and then we go back and delete, we get the D, and we print out D doesn't have any children, so we don't add anything, and when we delete, and it is a slash, and etc. Okay, so we can traverse the tree in the level order. Now we have 4 orders for traversal, and we have one example tree here. And what are the results of these 4 traversals? Okay, and you can pause and you can try by yourself. And pre-order will print out plus and star and A plus slash B C D minus E F. And if it is in order, it will be A star B slash C plus D plus E minus F. Okay, then if it is post, then it should be A B C slash D plus star E F minus plus. Okay, and the level order traversal will print out plus star minus A plus E F slash D B C.